report on circuits reports is to delve into the concept of circuits, predict circuit behavior, and explore the basics of building them. After this report, one should fully understand how currents flowing through a wire depends on various properties, laws, and such as Ohm's law and Kirchhoff's loop law. The behavior of DC and RC circuits using batteries, resistors, capacitors, ammeters, and voltmeters. We confirmed that in a series circuit, current remains constant throughout, and our measured current was 0.02 amperes. Using Ohm's law and Kirchhoff's loop law, we verified that the sum of the voltage drops across components equals to the total supplied voltage. In the RC currents circuits, we observed that the charging and discharging times increase with greater resistance, confirming that time is directly proportional to the resistance. Although the ideal model predicts instantaneous charging with no resistance, our real-world data showed a brief delay due to internal resistance in the circuit components. Electrical circuits. Electric current flows through a closed path made up of components like a power source, such as a battery, wires, and electrical devices like bulbs or resistors. Circuits can be arranged in two main ways: series circuits, where components are connected one after another in a single path, and parallel circuits, where components are connected in multiple branches. Understanding how electricity behaves in these circuits requires a few key rules, starting with Ohm's law. Ohm's law explains the relationship between voltage, current, and resistance, and is written as such. This means that the voltage across the component is equal to the current flowing through it multiplied by its resistance. Kirchhoff's loop law, which applies to closed circuits or loops. It states that the total voltage supplied by the battery must equal the total voltage used by all the components in the loop. In simpler terms, the energy you put into the circuit is completely used up as the current passes through resistors, bulbs, and other devices. This helps us to analyze more complex circuits, especially when there is more than one resistor or power source. Together, these laws help us design, understand, and troubleshoot electrical circuits by predicting how current and voltage behave through them. We must first clarify that several assumptions were made while collecting and analyzing data. We must assume that the atmospheric conditions, such as temperature and humidity, do not significantly affect the electrical components and measurements in the circuit. We must assume that all wires in the circuit are ideal, meaning that they have zero resistance unless measured otherwise, so they do not contribute to the voltage drops around the circuit. We must assume that the multimeters used as ammeters and voltmeters are properly calibrated and provide accurate readings without drawing significant currents or altering the circuit behavior. We must also assume that the batteries remain in a constant voltage output during the duration of the experiment, and the internal resistance of the batteries are negligible. Performed by assembling simple DC circuits using resistors, batteries, ammeters, and voltmeters. Following the series and RC circuit diagrams provided, we began measuring current through resistors connected in series using two ammeters, verifying that the current maintains strong constant throughout the circuit. We then converted one ammeter to a voltmeter to measure potential differences across the individual components. After confirming that the sum of the voltage drops equal to the total supplied voltage, we proceeded to investigate an RC circuit by charging a capacitor in series with a resistor and battery, then observing its discharge through a resistor. The total potential difference was 2 times 1.5 V, which is 3 volts. The total resistance of the resistors in series was 147 ohms, and using the calculation formula, we left with a current of 0.02 amperes. However, when we reversed the circuit, the measured current was 0.02 amperes, verifying the law that charge is always conserved in a closed loop. Additionally, if we replace an ammeter with a voltmeter, the ammeter left reads 0 due to the voltmeter's high resistance, but the voltmeter reads 3 volts due to no voltage drop. We proved this with the loop rule as well. We also noted that when measuring the time it took to charge and discharge a capacitor in an RC circuit, the time was directly proportional to the magnitude of the resistance of the resistor. Charge and discharge you can see it in the image over here, and you can see the relationship is a straight line, which means it's directly proportional. I had listed out some assumptions made in order to proceed with this analysis. These assumptions can also be presented as sources of errors. Thus, total sources of errors are inaccurate multimeter readings due to calibration issues or internal resistance, fluctuations in battery voltage during the experiment, contact resistance at wire connections and components terminals, human error in reading instruments or timing measurements, and idealized assumptions in simulation, that is, neglecting wire resistance or heat source. Is charged with no resistance in the circuit. The ideal model predicts it would charge instantaneously because there's no limit to current, there's no resistance to limit current. In real life, this doesn't happen. The charge takes a small but measurable amount of time. Using an ammeter, we see the capacitor still takes a short moment to fully charge due to internal resistance in the wires, battery, and ammeter. These non-ideal factors slow down the charging process compared to the ideal prediction.